Okay, Unit 9, Applications of Thermodynamics. We are on question number 16. Let's get to the questions. Here we go. Ooh. Okay, POCl, PClO2. Okay, we have a delta G that is positive, so that means, okay, this means alone that this is not thermodynamically favorable. A sample of POCl is placed in a closed rigid container at 298 Kelvin and allowed to reach equilibrium according to the equation above. Based on the value for delta G, which of the following is true? Well, if the, okay, all right. If your delta G is true, and then you see that E right there? All right. So that's not E as in electrons, that's E as in ln. So we're talking about delta G is equal to negative RT ln K, right? So if delta G is equal to negative RT ln K, let's get K by itself, okay? So here, let me move this so I can do a little bit of work here. I'm gonna have delta G. I'm gonna have delta G divided by negative RT. That gives me ln K. To get rid of the ln, I will set this to the power of E, or E to the power of, and then I will get K is equal to E to the delta G negative RT. Okay. All right, a couple things need to be done, and okay, a couple things need to be done, and I really shouldn't have written that E like that. It's more of an, it's an exponent. Okay, so gross. Okay, all right. Remember, your R. This is a key part to this question. How do I do this? Let me try to show you like this. Delta G is in kilojoules, and R is in joules, so you're going to have to mess around with that number. Okay, so if this is what I'm looking for, if this is what I'm looking for in that question, I see that I need 490 in the numerator. Okay, yeah? But so it has to either, okay, so it can't be this, it can't be this. It has to be either 490 or the 4,900,000, right? 490,000. Now, see that 8.314? They didn't, in either of these, they did not change that 8.314. They didn't change it here either. So in other words, instead of making that into kilojoules, they made the numerator into joules. That means the correct answer is A. They multiplied it by 1,000 to make delta G into kilojoules. And if you look at the question, they tell you that it's in kilojoules. It is kind of your job to know that the R 8.31 is in joules. All right, let's look at number 17. Okay, what's happening? The NO2s are slowly becoming N2O4s. The diagram above represents the gas phase reaction of NO2 to form N2O4. A certain temperature. Based on the diagram, which of the following best predicts the example of the sign of entropy change? What's happening in the entropy? There is less disorder, okay? The more things you have, the more collisions there are going to be. There's less things here. There's less collisions. There's less chaos. It's people staying home because of the coronavirus, right? So, all right, so your delta S is decreasing in entropy, so your delta S is negative. So you can already say it's not C, it's not D. It has to be A or B. Now, if it's between A and B, and we're looking at this and we're saying, okay, let's just read them. Delta S is negative because the number of N2O4 molecule increases as the N2O4 did not increase. Well, the N2O4 did increase, but that doesn't mean your delta S is negative, okay? Because if we added more N2O4, that would have been bad too. The delta S is negative because the number of molecules in the gas phase decreases. Yeah, the total amount. It's not about the amount of just the N2O4. It's about the total amount. So the correct answer is B. All right, number 18. Here is, if you need a review on the galvanic cell, I did a review on that on a separate video. Please check it out. But here you go. Cu plus Zn. This is the most famous battery of all time. The the E cell is 1.10. This is a galvanic cell. The reason I know it's a galvanic cell, there is a salt bridge. Okay, that's kind of the biggest thing. Above generates 1.1 volts for the construction. For the construction of a second galvanic cell not shown, one modification was made. The Cu electrode has doubled in mass than the Cu electrode in the first cell. Which of the following correctly compares the initial E cell for the second cell to that of the first cell? Okay, let's check out what's happening with the Cu. This is telling you that the Cu is gaining electrons, right? The Cu is positive and now it's becoming neutral, so it is the rig, okay? It is, in other words, the cathode. It is gaining electrons. So as electrons are going this way. That means the Cu2 plus in this solution is starting to become more Cu. And this, in other words, this electrode is starting to get bigger and bigger and bigger and bigger, and the mass is getting larger and larger and larger and larger. And the Cu in the Cu2 plus in this solution is starting to decrease. There's less and less Cu over there. That means this Zn electrode is our oxidation spot. It's where oxidation is happening. This is our anode. And the Zn is starting to shrink and shrink and shrink as the Zn is starting to become more Zn2 plus and more Zn2 plus. There's more and more Zn2 plus in here because these Zns over here are losing electrons, becoming Zn2 plus. Okay? So the Cu electrode is getting bigger and bigger and bigger. The Zn electrode is getting less and less and less. So the question says the Cu electrode has doubled in mass. Okay, we did the experiment 2 times. One time we had a Cu, and then second time we had a bigger Cu. What happens? Okay, the answer is D. If you increase the mass of the Cu, well, the Cu is not the thing that's decreasing, the thing that's increasing. It's just going to increase more. So the initial, it's going to stop when you run out of the Zn minus. The Cu is not the limiting. The Zn is the limiting. Or, and just think of it in terms of reactance. The Cu is the product. So the two things that can limit this reaction are the Cu2 plus and the Zn minus, and the Zn. Those two things can limit the reaction, but having more product, that's not going to limit whether this thing takes place. So the correct answer is in the D. The initial E for the second cell is the same as for the first cell because the overall chemical reaction occurs and the cell does not change. Yeah, why would the reaction change when our reactants stayed the same? Our product was the thing that changed, right? So no, the answer is D. Nothing changes. You just increased the product, not a reactant. All right, number 19. Okay, this is an IVR question, and I'm just not going to do it. Look, there's 2 IVR questions, and what I mean is I is equal to V over R. You can look it up. This is current is equal to amperes over volts, or resistance. But I'm just not going to do it. It's just not worth it. There's 2 questions in this entire packet. They're going to happen in the next one is like question 27. It's not a big enough topic in the AP exam for you to waste your time. You could look up a YouTube video on how to do an IVR question to do this 2 problems in an entire test. It's not a topic worth of my time. All right, so let's just get back. All right, number 20. Platinum electrode. There's a battery to another platinum electrode, and you have molten NaCl. I know for a fact that this is an electrolytic cell. You know how I know it's an electrolytic cell? There's 2 things. An outside battery source, and there is no salt bridge. Okay. There's no salt bridge. There's an external power source. This must be an electrolytic cell, meaning that your E cell is negative. And if your E cell is negative, your delta G is positive. It is not spontaneous. Okay, this is guaranteed fact, all stemming from the delta G is equal to negative NFE. Okay. All right, the diagram represents an electrolytic cell. See, I was right, even though I wasted all that time trying to explain it. But I'm trying to show you how you can just look at it and see what kind of cell this is, in which the reaction NaCl becomes 2 NAs and Cl2 takes place. The Table gives the relevant reduction half reactions and the standard potentials. Based on the information given, which of the following is true? Okay, now we gotta figure this out. All right, you're either gonna have negative 2.71 minus 1.36, or you're gonna have 1.36 minus negative 2.71. And I'm just gonna let you know right now, this guy right here cannot be. Because if that was the case, this would be a negative E cell. Like you'd have a negative minus a positive, right? So if this top one was it, then you'd have a negative, you'd have a negative E cell. No. Shoot, I just screwed up. Okay. That is it. Okay. It cannot be this one. The reason why it cannot be this one is because that would give you a positive E cell. Yeah? If that gives you a positive E cell, then that means you will have a negative delta G. And this already told us it's an electrolytic cell. Electrolytic cells are not spontaneous. This cannot be true. So this cannot be it because it would give you a positive E cell. Okay, this one on top is a negative minus a negative. That would give you a negative E cell, giving you a positive delta G. That is what you want. So in other words, this is your E cat minus your E an. Okay? So you're going to have to subtract those, negative 2.71 minus 1.36. That turns out to be like 4 something, 4.07. Ah, that's probably what it is. So just based on that, I can figure that out. That is C. Okay. Okay, so remember, this was an electrolytic cell, so I knew that the delta G had to be positive. That means the E cell has to be negative. So I just combined these two numbers in a way that would get it to be a negative E cell. Now, you can actually do it by looking at the diagram, but I think this is actually the easier way to do that. All right, number 21. H2O, H2O2, the reaction in which H2O is decomposed into H2 and O2 is thermodynamically unfavorable. Delta G is positive. See, you know how you know that this is also an electrolytic cell? There's a battery. There is an outside source of power. Okay, however, an electrolytic cell such as the one represented above can be used to make the reaction occur. Which of the following identifies the flaw in the representation? Okay, this was whack. I was looking at this for hours, and this is a very famous experiment of the electrolysis of water. Like you put the cathode is where you are gaining electrons, right? And the anode is where you're losing electrons. So hydrogen. Okay, hydrogen is the positive thing, right? Oxygen is the negative thing. So this side is emitting electrons and it's attracting the hydrogen. This side is taking electrons, like you're losing electrons here, because this is the anode, it is the oiling, it is losing electrons. So I was like, looking at it, I was like, this is perfect. And they even are showing it in a 2-to-1 ratio, right? And I was like, this is perfect. They didn't write this. I thought that was whack. And so the question says, okay, so then I finally read the stupid thing. Oxidation is occurring at the anode instead of the cathode. I was like, no. The reaction is not correctly balanced. No, the equation is it's not correctly balanced because it wasn't balanced. But I was trying to find it, and then I read the questions. And I generally tell you guys, read the answers before you do the problem, but yeah, I didn't catch that. All right, number 22, a little bit more straightforward of a question. Okay, it's asking for what the delta S of the reaction is, and the delta S for the reaction, delta S is equal to S final minus S initial, or S products minus S reactants. So your products, you have 2 times 330. Minus 2 times 310 plus 210. Okay. Now, Okay, normally I would just estimate these, but look, these numbers are super close. Okay, I mean they're a margin of 10, and I don't want to, I don't want to do that. So this is 660 minus 620 plus 210. This ends up being 660 minus 830. That becomes negative 170. The answer, B. Products minus reactants. Make sure that you guys are calculating for the coefficients. 2, 1, 2, right? So this is 2, 1, 2. And then just get them from the table. Products minus reactants, or final minus initial. 23. All right, I'm taking a look at this. I see the Fe2. Here is the HF. Oh, the one thing that needs to happen is this needs to be multiplied by 2. There. This is actually okay. All right. So, oh shoot, this is a neat question. If you remember what happens in your K values when you multiply it by 2, is it becomes K squared. So this is 2 times 10 to the negative 6. This is actually really interesting. This becomes 1 times 10 to the negative 6. Or sorry, 1 times positive 6, right? Then you're supposed to multiply these things. And then, so what is K3 equal to? It's kind of like Hess's law, but Hess's law, you add them. In equilibrium, you end up multiplying them. So this becomes 2 times 10 to the 0. So in other words, the K is 2. It's just barely over 1. K3 is barely over 1. So here's the answer. Okay, on the basis of the information above, the dissolution of Fe2 in acidic solution is thermodynamically favorable. The delta G is negative because the K is positive. Remember, this is referencing delta G is equal to negative RT ln K. Okay, so if your K is positive, look, it doesn't matter, your K is 2. It matters that your K is positive. If your K is positive, then your ln K is positive. Or sorry, not positive. If your K is greater than 1, then your ln K is positive. So that means overall, your RT ln K is negative because of the negative sign, and the delta G is negative as well. It is thermodynamically favorable. Notice that if you didn't know how to do that, these would not cancel out. So you would have gotten a negative number. You would have a K is less than 1. It would give you the wrong. It's such a smartly written question. Okay, 24. Which of the following processes would delta S have a negative value? Okay. Here are your grandparents. You have 2 grandparents becoming 4 grandparents and 3 grandkids. Okay? That's the way right? Gases are grandkids, liquids are, whatever. Okay, so you have solids becoming solids and gases. That entropy is increasing. Okay? So this would have a positive delta S. Okay? MgO8, Mg aqueous, 2 aqueous becomes 1 solid. So 3 aqueous things become 1 solid thing. That is losing entropy. It's getting less disorder. This is more chaotic. There's 3 things. Now it's only 1 thing. This is less chaotic. So that's a negative delta S. Then you have this side. You have 2 moles of gas. You have 2 grandkids. Okay, 2 moles of grandkids becoming 1 mole of grandkids. That's lessening disorder. The disorder is going down because 1 kid is less disorderly than 2 kids. So which ones did the delta S have a negative value? 2 and 3 only. There you go. Grandparents and grandkids is how I remember delta S. All right, let's look at this one. The oxidization number is represent. You know what? I did do what I'm about to do. Read the answers first, and I see, oh, delta S, delta S, delta S, delta S. Okay, let's first do that. What the heck's happening with delta S? We just did this. I have 4 grandkids becoming 4 grandparents and 3 grandkids becoming 2 grandparents. Look, once you get rid of the grandkids, right? Once you get rid of the grandkids, there's going to be a whole lot more order. Okay, so they got less disorderly. So your delta S is negative. So your delta S is less than 0. So you can cancel out C and D just right off the bat. Okay, so always take a look at how that's going to work. Okay, so now it says there are more Okay, explain whether this is thermodynamically favorable or not. And they also gave me my delta H. So I'm going to calculate delta G is equal to delta H minus T delta S. Now, we just said that the delta S is negative, right? This is negative. And the H is negative. All right. That means T is what we're depending on. Okay? So if delta H is negative and delta S is negative, well, if T is super small, like if T... Okay, if T is super big, okay, this T delta S trumps the delta H. If T is super small, right, then delta H trumps T delta S, okay? Look, this is trying to make the thing positive. It's a negative negative. This is trying to make the thing negative, okay? So who wins? Well, it depends on the temperature, okay? So there are more particles, including particles in the gas state and the reactants than in the product. Yes. Thus, delta S is less than 0. Because H is large and negative, the reaction will be thermodynamically favorable at low temperatures. That is true. When your temperatures are low, it's going to be... When your temperature is low, this thing doesn't count. And this negative makes sure that this thing stays negative. Okay? So the correct answer is A. And if you weren't sure, look at B. It says, because delta H is large and negative, the reaction will not be thermodynamically favorable at any temperature. No. If your temperature is super high, your delta S will overcome your delta H and it'll become positive. 26. H plus Cl yields HCl. The formation of HCl from its atoms is represented by the equation above. Which of the following best explains why the reaction is thermodynamically favorable? Okay, you have two gases becoming one gas. Okay, you have two bonds becoming one bond. Ooh, this. Oh wait, there's no bond at all. Formation. Okay. Okay, delta G because energy is released between the bond and HCl, H and Cl atoms forms. What? No, there is no bond in H and Cl, and it's going the other way. So this is wrong. Your B, delta G is positive, meaning it's not thermodynamically favorable. Isn't that just wrong because it tells you that the reaction is thermodynamically favorable? Yeah, so these are just wrong because they're saying that delta G is positive, meaning it's not. So it has to be between C and D. Delta G is less than 0 because although energy is absorbed as the bond between H and Cl atom forms, energy is not absorbed here. And formation is exothermic. Formation is exothermic. This is saying absorbed. There is energy absorbed when this is formed. No, energy is released when bonds are formed, so this is wrong. Delta G is less than 0 because although entropy decreases, it does decrease because you have two gases becoming one gas. Because the number of gaseous particles is less than the number of gaseous reactant particles. Energy is released, yes, energy is exothermic as the bond between H and Cl forms. So just remember that formation of bonds is exothermic. The correct answer is D. That's a lot to read, but hopefully I'm giving you guys ways to get through it kind of quickly. Okay, number 27 is the other IVR problem. I don't want to do it. It's, again, not worth it. If you want to look up how to do IVR to do both these two questions, then go ahead, be my guest. Let's not waste our time. Let's go to 28. Oh, you know what? I don't think you guys see a table that's supposed to be here. So you can't do number 28. So sorry about that. Oh, if you want the answer for number 27, I forgot the answer to number 27 was C, just if you guys ever want to check it. Okay, 28 we'll skip. There's nothing to do there. There's supposed to be a table here that I guess just didn't get printed out. Okay, and the electroplating of nickel. Ooh, this one is cool. Okay, this is how we do like when you see like a metal that is like we say gold plated or chrome plated. This is what we're talking about. Okay, so we have nickel sulfate in this question. All right. A 0.2 Faraday of electrical charge passed through a solution of nickel sulfate. What is the mass of nickel deposited? Okay, this was a really like crazy question. Okay, there is 0.20 Faradays, okay, in this question. You know what, let me shrink this a little bit. Okay, there's 0.20 Faradays in this question. And look, I'm just the kind of guy I'm just gonna try to get to grams, okay? I'm gonna just try to get to grams. And so I'm trying to think, and I'm thinking, and I realize that a Faraday, well, a Faraday is measured in moles of electrons, right? Or, you know, there's 96,485 coulombs per second. That's a Faraday. So, but anyways, there's 1 Faraday per 1 mole of electron. That's like kind of like this rule, okay? Now, that's something you kind of got to know, but what are you going to do? All right. But in this nickel, see this nickel right here? It's hidden with the SO4. What's the charge of that nickel? It's Ni2+. It needs to gain 2 electrons if it wants to become nickel. That becomes nickel-plated nickel, right? So, this is 2 moles of electrons. There are 2 moles of electrons for every 1 mole of nickel 2+. And 1 mole of nickel 2+ has a molar mass of 58.7 grams. And so I was looking at this and I was like, oh shoot, this is cool. Like your Faraday cancel out with your Faraday, your mole of electrons cancel with mole of electrons, your Ni2+ and your Ni2+. So 0.2 divided by 2 times this, that just becomes B. That's actually pretty simple. The question is, did you know a Faraday was equal to 1 mole of electrons? Maybe not. That's tough, but you'll get there. I don't think this question is very on the AP exam that much either. I just want to do them because they're kind of easy dimensional analysis ones that I don't actually have to learn a concept for. I just need to get to grams somehow. Okay. All right. Last one. You have K plus a Cl2 yielding KCl. The delta H is -437. Elements of KCl react directly to form compound KCl according to the equation above. The information table below answered already that question. Okay. It is observed that the reaction producing KCl from its element goes essentially to completion. So in other words, if it goes essentially to its completion, that means its K has a lot of product and not a lot of reactant. In other words, your delta G is absolutely negative, right? Your K is great. Your K is greater than 1. Which of the following statements is true about the thermodynamic favorability of the reaction? The reaction is favorable, maybe. The reaction is unfavorable, no. Reaction is favorable, maybe. Reaction unfavorable, no. Okay, now let's look. Okay, so we know, is it being driven by enthalpy? Hell yeah, it's driven by enthalpy because the delta H is negative. But is it being driven by entropy? No, you got a solid and a gas. You got a grandparent and a grandkid, yeah, becoming a grandparent. So in other words, delta S is negative as well. So your delta G is equal to delta H minus T delta S. If your delta S is negative and your delta S is negative and delta H is negative, and it's saying this is thermodynamically favorable, it's because it's saying that the delta G is negative, yeah? Well, what's helping it become negative? The delta H is absolutely helping this become negative. This is not helping it become negative because it's a negative negative. This is not helping. It must be at a low temperature. So what's driving this reaction? The enthalpy is driving the reaction, not the entropy. So the answer, the reaction is favorable and driven by enthalpy change only. A is the correct answer. Get out of here, C.